So, hello and welcome to the first session of ACCU 2023, which I'm lucky to be able to present now. So, here's my talk on removing needless, undefined behavior for a safer C++. Or as I've kind of retitled the talk, Addressing UB for a safer C++ after removing gratuitous undefined behavior from C++26. Just in case you don't know me, I'm Alisdair Meredith. I work in Bloomberg at New York as part of the BDE team. We write all the lower-level foundational libraries that do all the software things at Bloomberg that then build all the application domain stuff on top of. So I'll implement something like our own internal STL and so forth. And I've been a member of the C++ Standards Committee since coming to an ACCU conference where Francis Glasper said, you should really come to these standards meetings. And look, there was one in Bristol, in London, Oxford in 2003. I'll get the destination right. So yeah, I've been a standards member since ACCU persuaded me to join about 20 years ago. So what is this talk about? We're going to start with a discussion of what we mean by undefined behavior. And then we're going to have a look at some of the natures of different kinds of undefined behavior you might find in the C++ standard. Then we're going to talk about whether it makes sense to have undefined behavior while you're actually in the process of translating your program as opposed to running the program, and what that means and whether that has an implication on how we might think about the standard. I'm then going to look at some common sources of undefined behavior that occur in programs, and then how we might mitigate those in the standard, and potentially, looking ahead, some coming language extensions that might help in those mitigations. Why are we having this talk? Well, it's an uncomfortable fact that at the moment, C++ is under attack from a variety of sources, and we now have governments issuing directives, notably the US and the EU, that no new software should be written in either C or C++ due to various security risks. So unless there's no other viable language, the intent is all new software should now be produced in some kind of memory-safe language without specifying which those languages are. So as I said, the primary concern is security. This talk is not going to address memory safety. That is a much bigger topic than this talk will address. But it will address some of the other concerns that lead to those security concerns, which is the rampant effects of undefined behavior in the specification and programs today. And trying to contain that and bring that more under control than we feel is happening today. So I'm going to start by tackling what I believe are some popular myths regarding undefined behavior. Then we're going to demonstrate some inappropriate use of UB in specifying the standard that I believe should be specified in another way, and that's something we can fix for C++26, reducing that boundary of chaos in a language and then the security risks. And there's a variety of ways we can do that. We can either bless existing behavior or make it diagnostically ill-formed. But there's distinctly things we can do better than undefined behavior. And the ultimate goal that this presentation is going to get to is the idea that with some of the new language features coming in, there's a category of undefined behavior in the standard today that we should be able to do a much better job of identifying at runtime and controlling rather than going off into the wilds of unconstrained behavior. So I'm going to start with a quick show of hands on a couple of features to get our base level of knowledge of where we think we're coming from. Which of the following popular quotes do we believe is feasible for undefined behavior to do? The classic original coming all the way from the POSIX community, I believe, is cause nasal demons to fly out your nose. Who believes undefined behavior can actually do this?
It would be abusing.
But nobody...
Are we just talking about undefined behavior?
I'm running a C++ program, I hit undefined behavior. Can the compiler cause this to happen?
But this is
I'm seeing no hands, despite this being the typical quoted feature for undefined. I'm seeing one hand who's feeling vaguely bullied into raising a show of support.
I think this is all possible.
You think this is all possible? Okay. Popular quote from Marshall Cloud: "It could make my cat pregnant," which is a big surprise to the cat, but bigger to me because I didn't know I had a cat. Any takers? I'll presume an implicit hand there that's taking a photo of the camera at the moment. Launch a game of Rogue. I see a few more hands going up on that one. Okay. Time travel. Can your C++ undefined behavior produce time travel?
It would be nice.
I'm seeing a couple of hands in an expression, "it would be nice." Can it delete all the files on my hard drive? I'm seeing a few more hands going up on that one. Can it delete all the files on my customer's drive? A few more hands, okay. So my goal is to see how well we understand these terms, and do we interpret them all the same way? So we've been talking about undefined behavior. We also have the notion of unspecified behavior. Is that distinct from undefined behavior, or is it just as wild and woolly at the end of the day? Hands? Is this equivalent to undefined behavior, just written another way? I see one yes, a few uncertainties. You see, these are terms we should be clear about, because we're using these to say things, and if we're not as clear on the meaning, consequences happen, and this is part of why the reputation of C++ and undefined behavior being under attack. We need to be clearer about these terms than we have been. Implementation of defined behavior. Is that as wild and woolly as undefined behavior? It varies according to the implementation that's defining the behavior. Okay, I'll take that. An ill-formed program, I hope we all understand, is that program is not going to be a good program, and you'll get a diagnostic that tells you that. How different, though, is ill-formed with no diagnostic required to undefined behavior? Are these two stating the same thing? They're not the same. Excellent. How do they differ?
Well, on the last two, the compiler may not produce an executable at all.
So the claim is that ill-formed, no diagnostic required, the compiler is not allowed to produce an executable. Might not. Whereas for when you've got undefined behavior, you're required to produce an executable.
Yes.
I think that's a good distinction. Thank you. And you might have just cheated me out of some of my slides. So I'm going to go over some basic definitions that I think we as a community should be sharing and understanding and being clear when we start talking about undefined behavior in our programs. Which means let's start with, what is a program? The standard defines a program as one or more translation units that are linked together. So that tells me what builds a program. It doesn't tell me what the program is or does. So I'm going to say my interpretation is the program is the end product of that tool chain in a target environment, the produced executable code. We've got the tool chain that's going to produce that executable code. That's what the linked together part means. The translation units are my source code. But the source code is a recipe to make the program. It is not the program itself. If we're talking about a program, we're talking about the executable at the end of the day that's produced by this recipe running through the tool chain for a specific environment to produce a specific program. Does this seem reasonable to everyone, or have I already lost the audience with where I'm going? Okay. So that then brings us to what is undefined behavior. And the standard quite clearly says it's just behavior for which this document imposes no requirements. So clearly the standard is going to tell us what it means by behavior. No. So I hit the index to find out what kinds of behavior occur in the standard, and I kind of classified them mentally as conditionally supported, implementation defined, locale specific, undefined and unspecified. These are common terms that occur in the core part of the language. And these are all talking about generally what's happening at runtime while you are executing the program. On the library term, we've got default and required behavior. Those are just specifications about the library functions. They don't really come under the term I'm looking for here. And I couldn't figure how to classify on receipt of a signal, but it was clearly something that was happening at runtime because you don't receive signals at compile time. So my contention is that behavior is a runtime property of the program. There is no behavior at compile time because it's a runtime property. Yeah, we're going to talk about compile time. Oh, sorry, that's my bullets for what I've just been talking about. So by its nature, it's a runtime property. But because it's a runtime property, behavior is bounded to the execution of the program. It doesn't occur before or after the program. The nature of undefined behavior, we say it's got no constraints on the program. We're not talking about things that happen outside the program. We've got no business saying what may or may not happen there. By its nature, it cannot affect things your program cannot reach. So yes, it can control any physical devices connected to your execution environment. It can communicate with external processes and mine Bitcoin and loot your banks if it so desires, but it cannot dictate the phases of the moon unless we get some bigger hardware. So yes, as a compile time behavior, what really is it? Well, if behavior is a runtime property of the program, compile time behavior is runtime behavior. When you're initializing a variable or dictating control flow of logic, you could do that same logic at runtime. We're just caching that ahead of time as compile time behavior. So in that sense, compile time behavior is the immutable parts of your program that have no interaction with, don't act on inputs or data produced at runtime, that the compiler itself can reason about to do interesting things while it's compiling the program to produce the same behavior that would happen at runtime. It's an optimization, it's not a distinct phase in that sense. And if it starts trying to do things that have no runtime behavior intent, then undefined behavior or anything talking about behavior is probably the wrong term. Unspecified behavior, we're asking, does this have the same connotation as undefined behavior? In principle, there's nothing that says unspecified behavior in general shouldn't have undefined behavior. But in practice, there's no such thing as general unspecified behavior. Even though the term unspecified behavior is defined in a standard, whenever it's used, there is a specific behavior named that is unspecified. So you don't produce unspecified behavior. We talk about whether certain things, we talk about, I'll go examples because I'm struggling to generalize myself here. So examples. When we're talking about the order of evaluation of expressions, that might be unspecified. There's an order, you don't know what it is, but you can't do anything other than produce the order. So you've nailed down a subset of things that can occur. And this is implicit in every use of unspecified behavior in the standard. So there's cases where it might produce 2 or 3 potential valid values when it's trying to disambiguate and say, yes, these are all equally good. Well, which one is chosen will be unspecified, but it will be one of those valid values. It will not invent a value that's invalid. Whether 2 pointers compare greater or lesser when they're not part of the same object or array. There is now a well-defined, unspecified ordering of all pointers in your system. So it will give a consistent good behavior, but you, as the author of the program, have no ability to predict what that order is. You can just rely that an order is there. It's unspecified. It's unspecified whether or not a reference requires storage. So this is just a neat optimization. If I got a reference to a local variable, the compiler can completely allow the use of that reference because it's not escaping that function. So whether it has to allocate storage for that, unspecified. And again, we see in another place where a certain kind of function call is whether it is valid or unspecified. Whether it is valid or not, sorry, is unspecified, which gives you the option that if it's not valid, you're going to diagnose it. And if it is valid, you're going to do the obvious thing. But there's no opportunity in here for undefined behavior to creep in. So while there's nothing saying unspecified behavior can't produce undefined behavior, the nature of how we use it in the standard and its purpose, there's always a set of things that you can infer or imply, and it's chosen from a set that will hopefully not have undefined behavior in that set. And at the moment, nothing in the standard with unspecified behavior does indeed fall into undefined behavior. So as I said at the end, typically unspecified behavior is not open to introducing undefined behavior, typically. And all examples today. So what is implementation-defined behavior? Behavior for a well-formed program construct and correct data that depends upon the implementation that each implementation documents. So we had the question earlier, can an implementation say, well, my behavior is undefined, I documented it? Making this, in the abstract, indistinguishable from undefined behavior. And yeah, I'm afraid that's pretty much true. It does whatever the implementation says it does. If the implementation, going back to the library vocabulary we use of narrow and wide contracts, if it's got a wide contract and says, yeah, there's no preconditions on this, be a second, no preconditions on this undefined behavior, then yeah, there's no undefined behavior there. But if another implementation says, yeah, I've got this precondition, you know, don't pass me a null pointer. If you pass me a null pointer, you get undefined behavior, then undefined behavior has crept into this contract. In the worst case, the compiler might just say, yeah, you get undefined behavior, that's it, we're done. That's very unhelpful. Was it?
Just to say that there was one compiler vendor, it was for C, where in an appendix it mentioned all the implementation possible defined behavior for C, and then underneath each of it said using this. So it told you. I found very helpful.
So the comment was that, was it a C implementation you were talking about? Where they'd gone through the entire C standard, listed all the implementation-defined behaviors, and explained what they did in those cases. That is actually a requirement of the standard, the C++ standard. Implementation defines the vendor has to tell you what it's doing in these cases. How well you can read your vendor documentation and find all that, they're not all guaranteed to be in one place as they were for this C distribution, is less clear. There is an annex at the back of the C++ standard that lists all the implementation-defined behaviors. We don't list all the undefined behaviors. That's a more ambiguous set. So one of the things we want to do for C++26 is have a better handle on how much undefined behavior is in the standard that we're just not tracking. But the implementation-defined behaviors, yes, they are all well delineated in both the compiler and the library. So let's go back to our pop quiz, where I'm disappointed. You all already saw my slides or something. You've largely agreed with me. No, it can't cause nasal demons to fly out your throat because UB is not magical. Despite what Marshall says, we are bound by the laws of reality. We cannot make mythical cats pregnant. Launch a game of Rogue, I saw a few hands go up because, yes, this used to be the behavior of GCC up until 295, that when you dereference a null pointer, it would look on your system and launch a game of Rogue or NetHack, or maybe bring up Emacs with Towers of Hanoi. That kind of Easter egg was fun in the day, but it kind of violates our social contract with the compiler today. So they have backed that out as it was cute, but it was harmful. Can we do time travel? Yep, the standard explicitly calls out that it can do time travel. But I'm going to claim that that time travel is limited to within the duration of running your program. You can't time travel before or after the program itself is actually running. So it's not unbounded time travel. And this is a potentially contentious claim for the folks who believed in magical undefined behavior. I hope it's a reasonable claim for this audience. Can it delete all the files on my hard drive? Well, you saw the trick question coming. Not without help, because it's going to have to know where my hard drive is. It can delete all the files on my customer's hard drive, on the other hand, where the program itself is running. Oh, yeah. So we're going to have an example demonstrating time travel to delete all the files on my customer's hard drive. And I've taken this example from a blog by Theodoros Chasliankis. I'm terrible at pronouncing Greek names, I'm afraid. He told me the example predates him, but he has some really nice analysis on his blog going through how the different code generation occurs on different compilers and whether or not different compilers are going to delete all the files on your customer's hard drive with this example. So we'll start with some simple. The top part is the only part that looks like C++, because I think the original example was written in C. So we're going to include the appropriate header, have a type def to a function type, and then have a static internal linkage, function pointer, do something. Do something is zero initialized at program startup, so it's going to hold the null pointer. It doesn't have some unknown wild and woolly value. We're also going to have this, again, internal linkage, so it's not exposed to the outside world, function that will destroy my disk by using the unpopular system command remove -rf / remove everything from my root directory recursively. Not a good thing to run. We do not want to accidentally run this function. But for some crazy Easter egg, someone thought it would be fun to put this in your program, along with another function. It's never called. That just sets the function pointer for do something to destroy my disk. Now, because it's set in a function that's never called, that's fine, because we're never going to do this. But void never called now has external linkage, so it's a bit harder for the compiler to eliminate. And finally, we get down to main, where we return do something. Oops, this is undefined behavior, because do something is a null pointer. And dereferencing to call through a null pointer, that is undefined behavior. So we're going to look, yep, it was well defined here. It's got a good null pointer value. This is not at all undefined behavior. We've got this function here that's never called. But, well, the compiler can be smart and notice, the only interaction with the do something function pointer I see, other than this undefined behavior, one point in the program sets it to a value. Why don't I optimize that for you helpfully up front of the program and time travel that assignment? That may or may not happen at runtime, but it's the only change that ever happens to that pointer. Well, why not just use that from the get-go? So some optimizing compilers, notably Clang at the time of this analysis, but Microsoft and GCC didn't do this optimization and said, I'm going to promote that assignment, and because when you return do something, you have it's undefined behavior. You don't care which of those pointer values you got. And lo and behold, it's now off deleting all the files on my customer's hard drive. That's really not good. This is the worst unbounded case of undefined behavior in C++. But note, it's deleting all the files on my customer's hard drive because I wrote the stupid function to do so that the compiler could use. Compilers aren't going to invent these functions on the fly just to give you crazy code and go, ha ha, fooled you. They want you to use them. So there's a social contract between us and the compiler. But in general, there's nothing stopping them doing this other than common sense. And this sense is sufficiently common, I believe we should be able to rely on it. But let's tweak the example a little bit. Let's now say I have an if test to say, if you pass me any arguments on the command line, I'm going to return 42. It's the answer you wanted. And only if you call me without any arguments will I return this undefined behavior. Our program has undefined behavior in it. It cannot determine ahead of time whether or not that behavior will be invoked because it's a runtime condition based upon this if. And the standard has permission for time travel. Is it permitted to time travel this undefined behavior ahead of the if? Or is this, if we call it with valid data for a valid run of the well-formed program, guaranteed to run despite the presence of undefined behavior in the program? So I'll give you 5 seconds to think about that, and then we're going to do show of hands. Who believes this program is guaranteed to give good behavior if called with command line arguments? Show of hands. I see 2 or 3, 4. Who believes this program is fully allowed to transform and remove all the files off my customer's hard drive? I see about 2, 3 times as many hands, and there's a few hands haven't gone up. I believe, according to the standard, that when undefined behavior occurs, it's got all these properties. It's allowed to time travel back to the point where that undefined behavior becomes inevitable. But while I'm running through this valid part of the program, no undefined behavior has occurred yet. And as long as the whole program can complete without hitting undefined behavior, you are not allowed to break that program with your undefined behavior. So now, up until this point, the undefined behavior was not inevitable. Time travel can travel to here. We can still allowed to change that function pointer because this doesn't use that function pointer. But it's not allowed to move this code up to here. You're not allowed to change the behavior of a well-formed program running with good data. And this is an important distinction because when people talk about craziness of undefined behavior, and I say the nasal demons and so forth, we just drop into lazy thinking. We throw our hands up and say we cannot reason about this program because it contains undefined behavior, and there's so much undefined behavior in C++. I don't believe that's the case. So my thesis, undefined behavior and time travel still do not allow my bad program to start reading all the files on another computer or on the same computer before or after running my program. And it's not also not allowed to ensure all files are deleted if the RM command is killed. You know, it's with the program I've given, you're not going to have anything in here trying to do anything outside the bounds of the program that was running. It's picking up the behavior I put into the program. It's not inventing crazy, malicious features for me. And I believe this is distinctly the case for C++, and without this, you cannot reason about C++ in secure environments. So undefined behavior is essentially, it's a social contract. There's a large part of this that if you really want to say, I have unconstrained undefined behavior, I can do anything within the limits of what I can express to a program, whether or not that was written by the author or not. That's not what compiler vendors do, but it's really hard to write a social contract into terms of a specified standard. So say my notion is, you've got time travel is bounded. Its ability to affect the outside world is only ever by whatever's connected to that device. You do not have to worry about mythical things beyond reasoning. I say the compiler is not going to introduce novel behavior that you've not written into the program yourself unless it's explicitly expected to be helpful. It might introduce an abort to terminate the program. It might try to break into a debugger, which I'm pretty sure is not written in your code, but is a helpful way for the compiler to handle undefined behavior, saying, look, I've got a problem, I want to help you with it. It's not going to help you by destroying your machine, to say, you really had a bad thing there, pay attention. That's not a good alarm. And again, undefined behavior is often amenable to external tooling, like we've got these utilities UBSAN, ASAN, TSAN. Does everyone here know about those? I'm seeing nodding heads. Does anyone not know about those? Okay, I'm happy to go on. So now we get to the issues that I have with the standard. This is where I start talking about potential fixes. We have undefined behavior in the lexer. Well, how does this make sense? The lexer is the part of the compiler that simply concatenates text into tokens to say this is the tokens for the compiler to work on. That's not runtime behavior. Essentially, it's, this should be using a different term. And as it turns out, during C++23, we did an awful lot of work, specifically led by Corentin Jabot, who I'll be calling out on the next slide, so that we can treat C++ source files as if they were UTF-8. All compilers have to support a UTF-8 rendering, or a UTF-8, what's it called? Encoding, that's the word, yes, sorry. Don't get old, your brain starts going and words just drop when you're looking for them. But yes, so we'll be looking for, the standard requires that all compilers can support a UTF encoding and kind of assume it's a default. So the standard can talk in terms of UTF-8 and not have to worry about all these other crazy encodings and how things might get put together. So that simplified a lot of the causes and issues in the lexer. And there were just 3 cases left that Corentin has cleaned up, and his fixes for that are going to land in C++26. The next meeting at Varna in June, they've been reviewed by core, but because the last meeting was still sending out C++23, we weren't making any further changes. So yes, we know this one's happening. And the example of cases like universal character name is spliced across lines. We've got UO3, splice, 91. Why would that be? Well, undefined behavior makes no sense. And why is it not supported anyway? Well, the reason it's not supported is when we first specified the preprocessor back in 1998, which we drew from the C preprocessor, which was specified back around 1990, they just didn't want to overly constrain existing implementations and wanted to bless whatever their preprocessors did. And the way that wording entered the language, or the specification of C++ back in 98, was we deemed that was undefined behavior. Given our choices now, this can just be well-formed. There's no reason to disallow it or have different optional behaviors from compilers. Another example is when you're token pasting with, so we've got the concat macro to concat the underscore in front of the U, and that, when you do the concatenation, that wants to produce one token that's a universal identifier. It should just work. And similarly, if I've got an unterminated string, that shouldn't be undefined behavior. That should be a diagnosable error. We can't mythically put an extra quote on the end. We don't know what you were saying, but we've got an unterminated string. The program is lexing in a strange state, so not undefined, diagnosable error. And that resolves all the issues in the lexer. And I was looking further at the preprocessor in general. And my claim is that any use of undefined behavior in the preprocessor where you're just manipulating the source text and not doing anything at runtime should be ill-formed, no diagnostic required. As I said, the key distinction between ill-formed and no diagnostic required is you're not required to produce a program. But the other issue comes back to time travel. We've got no bounds on the whole program. So effectively, your time travel is distinctly right back at the start of the program. There's no bets even from when you start main. There is no good data to run this program with. So ill-formed, no diagnostic required is strictly stronger than undefined behavior. But as we go through these 9 different undefined behaviors, we might be able to find, again, why are we not diagnosing it here, just force it, or, again, support that behavior. So I just got one example. So if there's a sequence of preprocessing tokens within a list of arguments, so we're expanding a macro, we've got a bunch of macro arguments that would otherwise act as preprocessing directives, the behavior is undefined. Now we're saying, the program is ill-formed, no diagnostic required unless we want to nail it better. What's an example of this? Well, in order to get the preprocessor directives into the argument list, you see we're just going to have to split our macro invocation across multiple lines. And yes, I have seen code that does something like this. In this case, I'm checking for the preprocessor definition of are our value references supported to pass either a tref or a const tref to either get a forwarding reference or a something that will bind in C++03. And of course, GCC, Clang, and EDG all accept this program today. Microsoft tell me that's an error. So this is no longer, Microsoft used to accept this until they got enough feedback that their processor was non-conforming, that they went away and did a special project to fully upgrade the preprocessor. Along the way, they diagnosed every undefined behavior in the preprocessor. So if we say it's ill-formed, no diagnostic required, no compiler has to change, I'm not sure that's helpful, but I'm not sure what the right answer is yet. But I just know something has to change here. So this is the kind of issue that we want to be addressing, that we don't want wild, unconstrained, undefined behavior in the standard. Simple things like translating code should not produce undiagnosable errors. But there's other ways we can have the preprocessor injected in here. We can, a hash line. So it's in the general, look for the general case. Yep, same set, accept and reject. What about if I try to do a hash include there? Yay, everyone rejects it. Unless I remove the closing paren, when GCC says, that's how I expect you to write your file you're going to include here. So it would be nice to identify a little bit better what we expect to be happening here, but I don't expect it's a common case. If we change this and make this ill-formed today, I guarantee code will break. Or is it broken? Because that behavior is undefined, whatever that means. So, looking ahead for more active ways we can improve the standard. One of the big papers that's being debated at the moment is originally from Jeff Bastien, who's chair of the Evolution Working Group. Uninitialized local variables are one of the major sources of security leaks. Because if you do not declare your variable, do not initialize your variable that's got a trivial default constructor or is a scalar type, it's not initialized at all. It has an indeterminate value. And accessing that indeterminate value is undefined behavior. Commonly what happens is, when it just creates a stack, there'll be some memory there that's got some garbage value, and whatever that garbage value happens to be is probably what's going to be read when you read that variable. And commonly security exploits arise when a smart user of your program can say, if I call this with just the right data, this will leave the value I want on the stack that will then cause the program to call into something that I control. This is best expressed, of course, when it's a function pointer, so you've got arbitrary hijack, but you might still be able to find other ways to inject malicious data to bring your program under the caller's control. And that's bad. And this occurs far too easily in C++ today. So one of the things we could do is try to propose a specific initialization for those local variables. Now, if they were global variables, we've already tackled that. That memory is zero initialized. So there's no ability to inject such hacks into global data. We've mocked up compilers that do this for all their local variables. Seems to work fairly well. Many programs that assumed this was the current behavior suddenly become correct rather than undefined, and that's good. But it's also masking opportunities where compilers have been warning you potentially today. Say, hey, you're using an initialized variable. That's undefined behavior. If we now define that behavior, we're taking away an opportunity for compilers to warn you about your bad code. So have a quick example. Talk about here, import std, so I've got access to everything. Int name, int x, I've not initialized it. So when I send it to cout, and the OStream operator tries to serialize that value out to the environment, well, C++23, x has an indeterminate value. The compiler is likely to warn me about this, but my program has undefined behavior. It may or may not write out something. It's undefined behavior. I say it's unlikely to do crazy things, but you have no way to predict what this program is going to do. With the C++26 proposals, x has an unspecified value. That means the value is valid but unspecified. It comes from the range of things representable by integers. But it also has a value. Successive reads of x will give the same value. And if you think successive reads of x might give different values, it is not possible. That's a popular optimization when you can say, well, this variable is not defined until later in the program. I can just assume it's a value in a current register. And register values change, even though the memory that will be ultimately occupied by x doesn't change. So, yes, without having a specified initialized state, x truly is indeterminate. So this program now has well-defined behavior. It will return 0, or whatever value we decide x should have. But now this program has well-defined behavior. The compiler is not able to warn you that you're using x without telling me what value that is supposed to be. Was that an intentional, I want x to be 0 or some other value, or was that a bug that is now not easy to warn about? So there's concerns that making this too well-defined is actually going to be counterproductive to the community at large by removing some useful tools we have for spotting buggy programs today. I could probably alter the order of the next two slides, but here we go. This is my thinking. This hasn't been presented to the committee yet, but function pointers are particularly prone to hijacking because there's other contexts where pointers, such as, if I call my constructor to my class and my class doesn't have a member initializer for my pointer, then it's still going to be left in an indeterminate state, even if we accept everything that the proposal from JF Bastian and others has. So perhaps function pointers are more prone to hijacking, and we should be explicitly at least always zero initializing function pointers as if they had a user-defined constructor. You can then make the same claim for object pointers, but in practice, function pointers point to something that was determined at compile time. That functions do not get generated at runtime so often. They might get unloaded if you're using dynamic libraries, but generally function pointers are stable. You might be mitigating the the problem with object pointers to say this is now at least pointing somewhere, but you have much more issues with pointers leaking and so forth. Are you just trading one form of bad behavior for another? It'll bring some level of sanity. At least a null pointer is something that you know to check for, as opposed to an unspecified dangling pointer you don't. But does that make progress forward, or are we just trading? These are questions that we still need to consider. And again, I was hoping maybe we could go further and emulate all indeterminate values, so that we take this proposal to every time an object is initialized, so even in the your constructor member initializers, just zero initialize the whole object in every context, and then start running the constructors. But does that have too large a cost? Initializing a pointer or two is not terribly expensive. Initializing an array of 1,000 pointers might be more than you want to pay up front. And again, we might therefore introduce a syntax to say, defer initialization, but I will request it. By the way, this is tackling the area of how can we reduce one of the more pernicious areas of undefined behavior in the language. And there's actually a paper now by Jake Fevold that you will find on last mailing, P2754, where he goes through a bunch of different possible ways that we might try to tackle this problem. So always zero initialize. It's viable because it will not break any existing code today. It's backwards compatible. And its expressibility of what's happening is worse because you lose those warnings. We could have either zero initialize or diagnose if you are trying to access an uninitialized variable. It's unclear whether that's viable because can you track down all uses of uninitialized variables without solving the halting problem? You can solve some. So it's not, needs more work to do if that is viable. It's backwards compatible for all correct code, because again, you're running into undefined behavior if you broke these rules anyway. And that is trying to basically get the same benefits as the first solution without changing the ability for the compiler, therefore, to diagnose and detect misuse. Because force initialization is forced to say, no, you're not allowed to have uninitialized variables at all anymore. That's a viable approach. But it's not at all backwards compatible because that code exists today, and we're saying that code, when you see it, is broken. Go and fix it. So although it's viable to implement, it might not be viable to ship. But it's clearly got a better expressibility because it forces you to express intent as to whether that data was initialized or presumably will introduce an annotation to say, well, that's the second example, an annotation to say, don't initialize this variable. This is the special case where I don't want to initialize my array of 20,000 ints. We've got another notion that we force a default value in there so that the UB is a little bit constrained, but it's still undefined behavior. Can't remember how this analysis went. It's come down as non-viable. So he must have some, part of that analysis must refer to how he is producing the UB.
Yeah, it's still UB.
Sorry?
It's still UB, it's solving.
But it's saying it's non-viable. It's not something that can be implemented. So I'm trying to think about, I'll have to go back and look at the paper for what this specific form of default that still UB was producing, that produced backwards compatible code with the same expressibility and some hopefully improved safety, but he determined that was non-viable. It was the only one that was clearly non-viable. Then we've got the notion of a default value with erroneous behavior. Now, erroneous behavior is my next slide. It's a new term that's being discussed to say, this behavior is bad. It's going to do bad things. But we don't want to say it's undefined because we don't want to have that kind of risk in the code. So it's going to behave badly in some way, but not necessarily in an undefined way. And the last one was essentially my proposal to always just value initialize, replace default initialization, where you can have these uninitialized states, with value initialization, which is you produce the default value. The viability of that is unclear. Not sure why, but the backwards compatibility is unclear. It's clear going to be backwards compatible, I believe, because this was undefined behavior before, and now you're just saying what those values are. But the cost is clearly prohibitive when you're now doing this on all objects everywhere. And again, the expressibility, I believe, should be worse, just like always zero initialized, because it's effectively doing the same thing. I'll have to have a word with Jake about that and re-review his value initialized only options. But what would you mean by erroneous behavior? This is a suggestion from Thomas Koppe in a paper that's been distributed around the working group when they were at the ACCU meeting, but has not yet been published in a mailing. This is behavior that's clearly wrong. We know we don't want to support that behavior, but we don't want to invite the full wrath of undefined behavior as well. So we're trying to narrow it down within the standards. So we're going to use this example of uninitialized or accessing indeterminate data, but it's a category of behavior we could use elsewhere as well, such as integer overflow and so forth. So the behavior would be essentially implementation defined. It may vary with your build flags or compiler modes. And things your vendor is likely to constrain to is it may be contained to providing a predictable value, which is one of those options we were looking at, but you can't rely on it. It might provide an unpredictable value. We're not even telling you what that value is, but it will be consistent. Or it may still unleash full undefined behavior when you want to build in a production build that optimizes the bells and whistles. But the intent is certainly you want to be able to have these options guaranteed available when you're doing your development. And that would be erroneous behavior. So I'm going to take a quick drink. So other places in the language that we could just say, rather than UB today, could be ill-formed diagnostic required. So this is just hunting through the standard to say, can we be clearer about our existing specification? So here's an example of a precondition in the core language. Two unsequenced operations on the same variable, or it calls it a memory location in the standard. I'm naming it variable here just to be more familiar. Our undefined behavior, whereas two unsequenced operations on different variables, so different locations, that's the key to enabling vectorization optimizations. So we don't want to lose the notion of unsequenced operations, but it's just saying if these two things are happening before or after at the same time as each other, and they're both manipulating the same variable, memory location, that's undefined behavior. So a couple of examples. I equals I plus I. Now the I and the I plus I are sequenced. This side is evaluated before this side. That has been true since C++ 17. I'm calling it out because not everyone's fully caught up on that, the deterministic sequencing yet. But this I++ and this I, their evaluation is unsequenced. And I look at that, and I can see that. The compiler looks at that, and the compiler can see that. So why is that undefined behavior and not ill-formed? This seems like the kind of thing we should be able to improve. Likewise, J is a reference. So I'm now looking outside my current scope to see what came in, but I'm manipulating the same entity, so deterministically I can see that's undefined behavior. I have a question.
How does this come into play with alias analysis, escape analysis?
Sorry?
How does this come into play with alias analysis?
How does it come into play with alias analysis? An excellent question. J and K are both references to ints. We do not know if J and K are aliasing the same thing at compile time. We cannot make that ill-formed. So we cannot completely eliminate this unsequenced, undefined behavior. But we can make progress, and I think we should. I hope today compilers give warnings here. I should have probably tested that out before I came to give the talk, but I believe many compilers will give warnings here. Certainly if they give warnings in this case, I hope they give it in that case. So, another precondition in the core language. If the object being deleted has an incomplete class type at the point of deletion, and the complete class, when you see it, turns out to have a non-trivial destructor or deallocator function, the behavior is undefined. Why do we ever want to support this? I have no use cases. If you have the use case I am missing, please tell me. So how much code would break if we made this ill-formed? Well,
What's the quantity?
none, as the existing code relies on undefined behavior. And undefined behavior means it can't be broken, we're just picking a different resolution. Unfortunately, there is well-defined behavior that you can't distinguish. That is well-defined code when the thing you're deleting actually is trivial. But why would you want to support just that special case? So my suggestion is it's probably ambitious to make that ill-formed in 29, but we should at least deprecate it. And then see if we get too many complaints about, hey, I'm using this with trivial types all the time. But, well, you're never going to get an incomplete integer. For the purposes of this, you're never going to get an incomplete enum. It's specifically on class types. So how many people are creating that many trivial classes that this becomes a concern, that they need to support it? So moving on to what I think is my bigger insight here. C++26, contracts are coming, we say again. SG21, it's working hard to produce a contracts facility for C++26. For those of you who are following C++20, you know for a really tantalizingly brief time we actually had contracts in the language. And this work is inspired by that proposal. But they've gone back to basics to build from the ground up, getting input from a much broader community to say what kind of features do we really need the contracts facility to address, what kind of problems does trying to address, introduce that we want to say, no, those specifically should not happen. So we've saying we've got a goal, we know what it kind of looks like, but let's go from the ground up and see what we can produce in time for C++26. So the aim is C++26 will have a minimal viable product for contracts. That's a feature that at least expresses at the minimum the ability to document preconditions and postconditions, run in checked and unchecked modes, and have a non-exhaustive set of behaviors that can respond when a violation of the preconditional postcondition is detected. And the minimal viable product is intended to say, we can enhance these in the future. All our future ideas of how we want to nail down or add more facilities here will be forward compatible. So nothing introduced at this point will inhibit further evolution. We know this is not the end point. So an example. Just want to avoid integer overflow. This is how I might write it today. Int checkable plus, int a and int b. Preconditions that check that I'm not going to overflow or underflow, in which case I can then return a plus b. Nice and simple. In contract forms, it would look something like this, although do note that the annotation syntax is still very much up for discussion and will not be resolved for a couple more meetings. What will be resolved at the coming Varna meeting is the range of responses to violations, so violation handlers or whatever we end up calling that part of the language. So it's simple. We now put the preconditions on the function signature so the compiler can see and reason about them more easily earlier, but it essentially looks the same. Actually, I'll go back to that. So yeah, but this now gives us a chance to go into whatever are predetermined. I've spotted that something has occurred out of contract. I'm going to give the compiler a way to deal with that rather than just saying hands off undefined behavior. The compiler is not allowed to optimize past these because it's got to be able to perform these evaluations to say, ha, I spot you have undefined behavior if this overflows. No, you can't flow past my attempt to detect that, even if I'm in an unchecked mode, because I want consistent behavior of the program. So my thought looking at the language is that contract violation stuff. There's quite a few things in the language today that read like they're specified as if they had preconditions and postconditions, and they produce undefined behavior. If we can land this contract facility, why wouldn't we use this violation handling process without having to annotate the language. The contract is in the core specification. But if we spot a violated contract, why can't we go into this facility rather than have wild, undefined behavior? So, sorry, I'm just a small brain fart. Don't get old. So in general, there's several kinds of undefined behavior that we're going to see as potentially preconditions. And the valid range of the operations are defined, so you can test that you're within range before you perform the operation. And calls outside the range of undefined behavior go into our contract facility. As I say, it's a bit like putting UB-SAN into the language. You have the ability to go into a mode that says, I want those contracts checked at runtime. And that's potentially expensive because some of these things happen all over your program. So you definitely want the ability to turn those off and fall back on crazy undefined behavior because you're not checking them. But it gives you a much safer domain to run and test your programs in. And I expect if we want to be able to turn these on and off, we're going to want something fine-grained, because integer arithmetic is something that happens a lot more often than some of your other operations. So I've got three notions of undefined behavior here. Preconditions purely in the arguments. They're easily validatable. They can use what I'm proposing here. And we could probably come up with a new term for these, like erroneous behavior, to say these are the things that can be checked with the contract facility. There's a deeper set that analyzing, say, is this a valid pointer? I can't do that just from a look at the pointer. I need to know what it means for that pointer to be valid and there to be a live object at the other end. That's going to require much more instrumentation and telemetry in my program to be viable. So these kinds of things that require much deeper analysis, they go beyond the domain of what we can reasonably do. But there may be ways to tackle them if somebody's particularly determined. I don't think we should require that. And then we get the intractables, such as general race conditions. I don't know if we're yet in a good place to start solving these problems well enough that we can specify in the standard that this will always be caught. So I'm basically talking about just this first bullet. So as an example, let's go back to our integer overflow. Int checkable plus, well, there's this function that's in the standard implicitly that does this. No, it's not recursive. The compiler magically will do the right thing on that plus. And this has that same undefined behavior. If this overflows or underflows, you get undefined behavior. So what if we treated this as if it were declared this way? I think that's an example of, hopefully good progress. Another common example, dereferencing a null pointer. We see this all the time. Simply put a precondition in. And that's, again, the built-in primitive. Treat it like it were contracted. I think this will hopefully solve a wide variety of triggering undefined behaviors today. But we don't have a solution for this one, as I was saying earlier, where in general we can't determine if P is valid. It could be pointing to something that's in dynamic memory and been destroyed already. It could be pointing to something on a stack frame or a long deleted stack frame that has now been reused. So in general, I don't think that one's tractable. But compiler vendors never cease to amaze me. Another example, if during the evaluation of an expression, the result is not mathematically defined or in the range of representable values, the behavior is undefined. What could go wrong dividing two floats? Well, clearly we don't want b to be equal to 0. That would be really bad. That will give us an undefined, unrepresentable answer. And we also don't want the exponents to produce something that overflows, because overflowing your range of representable values in a float does not produce infinity, it produces undefined behavior. Because infinity does not behave like a well-defined value. You're changing your behavior if you do not produce a value, but produce an infinity instead. It might happen on some implementations, or it might do nothing. It's undefined. So let's at least put that into contract. So this is a variety of the undefined behaviors. I took a quick sample from the standard. There's probably about as many more that I haven't listed. So floating point conversions. If I try to narrow a double to a float and I can't represent the value, that's undefined behavior. Likewise, if I try to go from a 64-bit int perhaps down to a float that's too small, conversions the other way, if they're not precise, again, undefined behavior. Bad values for enumerations. So the enumeration is determined by the lowest and the highest enumerator, which might not allow the full range of the underlying representation. Values that are outside the defined enumerations are undefined behavior. Throwing from a deallocation function. So I call delete, and delete throws, because I've written a class-specific operator delete. And that's undefined behavior. I was going to give a nice example about this until I realized when I wrote it that deallocation functions have an implicit no except. So most times that you try to throw from a deallocation function, you're going to get a well-defined terminate. But if you're determined and put a no except false on your deallocation function, you can throw from it and have undefined behavior instead. Perhaps we can do something more about that as well. Forming a null reference. You want that error when you form the reference, not when you try to use it. Using a null pointer to member, which is essentially the same as the null pointer example. Flowing off the end of a function that is supposed to return a value. We could just put a contract check there. So, oh, you got here. Before we leave, we're going to go call our out of contract handler. And in C++23, we also introduced I can't remember the name of the function off the top of my head now, a function that you can put in that's essentially telling the compiler, this code is unreachable. So it can make the assumption that you believe you've handled all your returns, so we don't have to solve the holding problem to determine that you've got a program that does flow off the end. But being able to put the contract check in at runtime rather than compile time is helpful. And again, C++23, we added the assume attribute that says, I'm going to assume this and not check it. It might be nice to be able to turn on a check that says, no, in my debug builds, I really still want to check that's true, even though I know in my production builds that has to be assumed. So I'm running a little bit faster than I thought. When I ran through this in practice, it went about 70, 75 minutes. It's run about 65. So we've got plenty of time for questions. But my summary is, undefined behavior is bad when it occurs. When it doesn't occur, it's not a bad thing. Our programs are tractable. There's more latent undefined behavior in C++23 that is helpful. And there's a bunch of ways we can go through and process the standard and mitigate those. And the pending contracts facility in particular gives us a neat way to be able to catch at runtime in a well-defined way, but potentially expensive way, some of those undefined behaviors. And, but in general, I'm not solving undefined behavior. I'm containing it to the point we can start reasoning about it. And the ability to reason is what brings us into the domain that you can start talking about secure programming. And that's my talk. Thank you.